Okay, I'll be ready in just 1 minute. Just trying to get my screen set. High technology here. Okay, I think I'm ready. The beauty and the power of the universe. Hi, I'm Walt Windish, and usually I'd be up in Jenny Jump giving this talk, but due to the stay-at-home, we'll be doing this on Go Live, as you know, since you're here. Good news is you still get the talk. The bad news is we don't get to go out and stargaze at 9 o'clock after the talk's over. Just one thing in my bio. I'm from NJAG, North Jersey Astronomy Group, and the Rockland Astronomy Club. Those are the two clubs I belong to, and been members for quite a while. So the talk I'm going to do is the beauty and power of the universe. And it's really just a survey of some of the stuff I like to talk about. And the overarching theme here is both beautiful and powerful objects. So I'm going to take you on a tour of some of my favorite objects in the universe. And I hope you'll take a look. I'm not going to go in depth. I've got a lot of slides. It's my hope that you'll Google some of these objects and get interested in astronomy yourself. I'm also going to take you on a little time traveling. So do you have any idea how I'm going to take you time traveling? Well, I'll tell you. I'll give you a hint. This picture that you're looking at is the Ring Nebula. And this object is 1,630 light years away from Earth. So what does that mean? It means that it took light from this nebula 1,600 years to reach our eyes, or in this case, the camera. So what we're looking at is how this object looked in the year 390, the Earth year 390. So the telescope's going to be our time machine. When we look at an object that's 5 light years away, we're not seeing it how it looks today. We're looking at how it looks 5 years ago. And the stuff we're looking at is going to be much further away than that. But there's some close-up stuff. To give you an idea, that the sun is 8 minutes away from us, light year wise. And since the moon is only 239,000 miles away from us, and light travels at 186,232 miles per second, the light from the moon is only about a second old. Unless, of course, you consider that the light from the moon actually came from the sun, and then you got to stick the other 8 minutes on. The farthest known galaxy in the universe that we've discovered is MACS 0647. It's 13.3 billion light years from Earth, and it's believed to be formed about 420 million years after the Big Bang. So the light from the galaxy has been traveling towards us for most of the entire history of the universe. Now, before I get on to most of our objects, I just want to explain to you a little bit about magnetic spectrum. I'm just going to take a shot, see, yeah, okay. Just making sure it's coming out on the screen. So the electromagnetic spectrum covers everything from radio waves to gamma rays. And we only see a little part of it. I don't know if you can see this on your screen, but the visible light spectrum is just in the middle. It's just a tiny sliver of the entire electromagnetic spectrum. And astronomers have instruments to study the entire electromagnetic spectrum. And each type of radiation gives us different information. Like we have a big radio antenna that we listen to Jupiter on radio waves up at the observatory, and that would be towards the right end. As you get closer to the visible light, there's a lot of infrared observations that astronomers make because they cut through the dust. And then as we go past the visible light, we get to smaller and smaller wavelengths that are becoming more and more powerful as far as the energy that they contain. So that's the electromagnetic spectrum. I think it's best just to give you an idea of what that means to astronomers. I could spend a whole hour just on this object. It's very interesting. It's a protostar, and it's in the upper left corner. And it's totally hidden by dust in the visible region. And so the only way that we can see it is by using an infrared sensor. So this picture was taken by the Spitzer Space Telescope. And matter of fact, it was just decommissioned this January after 17 years of service. It was a really special instrument, but it had to be cooled to about negative 400 degrees. So when the liquid helium ran out, they could still do the shortest wavelengths, but from 2009 to January of this year, they were doing what was called the warm mission because they ran out of the liquid helium to cool the camera, and still were able to get another 10 years out of the telescope. But it provided us with a lot of information through infrared sensors. And this is just one of the pictures where we see the Herbig-Haro object. It's a bright nebulous region of gas and dust, usually buried within dark dust clouds. And they're formed when supersonic gas ejected from the forming protostar, or embryonic star, interacts with the surrounding interstellar medium. And these types of young stars are usually only detected in the infrared. This is just another view of HH 4647. This is 3 different telescopes, information combined to make this one. This next image, the Eagle Nebula, or the next object actually, is the perfect junction of beauty, power, and space travel. So this is visible light image of the Eagle Nebula. The Eagle Nebula is about 6,500 light years away in the constellation of Serpens. And it's basically a star factory. That's why it's also known as the Pillars of Creation. Right, so the first step in the formation of a star is that some of this gas here starts to get enough gravity that it collapses under its own gravity. And as they collapse, they heat up. If there's enough material, that cloud will get so hot, it will ignite and burn under nuclear fusion. And then a star blinks in, it becomes a protostar, and then it blinks into existence. And so here we see stars being formed out of these dust clouds. The tallest column here is about 4 light years tall. So it takes 4 light years just for the light to go from one end to another, just to give you an idea of just how massively huge this beautiful object is. And again, this is a visible light. So it's pretty close to what you should see, except that cameras can gather a lot more light than your eye. So a camera will get a more detailed picture. Your eye is like a shutter speed of about 1/30th of a second. And if you point that in at this object, you're not going to see a whole lot. You might see the faintest white blur, but you need to keep a shutter open for a while to gather enough light to see something like that, even in visible light. But compare this photo with the exact same photo taken with the Hubble Space Telescope, which this one was, but using the infrared instruments. Totally different picture, isn't it? This is being taken in the near infrared area of the spectrum. And so you could see a lot of that dust is cut right through in infrared, and you can see just how many stars there are in this field. Very different information. Obviously, both photographs give astronomers useful information, but they give very different information. And that's why it's so important to take photographs using all different instruments and different spectrums. Here's one more picture of the Eagle Nebula, but it's a much wider view. Now, can you pick out the Eagle Nebula? It's right here. So this, you can see, this is a much wider view. The view we're looking at right here is about 70 by 55 light years. And you can see above the pillars a very young and hot star cluster, NGC 6611, and it's visible with modest backyard telescopes. And this star cluster is sculpting and illuminating the surrounding gas and dust in a process called photoevaporation. So I don't know if you're familiar with the hoodoos in Bryce Canyon, but those rocks didn't grow up from the canyon floor. There was erosion that took place and left those columns. And that's exactly what's happening here. You're getting photoevaporation from this intense radiation falling down. Not only are the winds blowing the dust and gas, the looser dust and gas away, but it's also illuminating this. So just to give you an idea how powerful the radiation is coming from those stars. Right? Again, we're talking 3 to 4 light years. And so stars that are about the same distance away are so bright that they're affecting dust 3 to 4 light years away. Here's a real interesting piece of information about this. Earlier mid-infrared images from the European Space Association and NASA's Spitzer, and also XMM Newton data, has led astronomers to suspect that one of those massive hot stars in that cluster, 6611, may have exploded in a supernova 6,000 years ago. And if that really happened, well, then the shock wave totally wiped out those pillars. And those pillars are no longer standing. But because the Eagle Nebula is 6,500 years ago, and astronomers think that the explosion happened 6,000 years ago, it's going to take us about 500 years to see if the scientists were right. So sit tight and we shall find out. But that's a great example of the time travel element. Those pillars may not even be there, and they may not have been there for thousands of years. And we're not going to find out until 500 years from now. So that kind of combines the beauty and the power and time travel all in one object. The rest of the objects we're going to take I'm going to take a look at a couple of solar system objects, and then we're going to go to the interstellar objects.
That pointer doesn't work.
Okay. Okay. I bet you know what this is. This is a comet. And comets are usually part of our solar system, gravitationally anchored to our sun in an orbit that takes them far away and then back to our neighborhood as they go around the sun. Now, I had to add the word usually just a year or so ago because we found some comets. We found a comet that visited us from interstellar space that was not part of the solar system. And since then, we have found another. And they're on a parabolic orbit. So they come in, go around the sun, and then they leave our solar system completely. Most of the comets go around our sun in an orbit, like this comet, Hale-Bopp. Hale-Bopp has a period of about 2,533 years. So it was discovered in 1995. So figure another 2,500 years it will return. The nucleus of Hale-Bopp is about 25 miles across. And I loved Hale-Bopp. I photographed Hale-Bopp up at the observatory in the 90s and just had a great time as it crossed the Perseid double cluster. And I was only bothered by bears once. So that was a good thing. You'll notice two distinct tails. That's what's so great about the Hale-Bopp. You saw both tails very distinctly. The blue tail is a gas or ion tail, and it's the lighter material, and it always points directly away from the sun. So you can follow that into where the sun is, wherever a comet is. If you find the ion tail, you'll notice where the sun is pointed towards. Now the other lighter blue tail is the dust tail, and those particles are heavier and they're not as affected by the solar wind, but they're affected by the motion of the comet. So the comet in this case is moving down towards the bottom of the screen, and that dust tail is following. Now, the reason why I introduced comets is because there was a real powerful display from a comet a couple of years before that, in 1993, a comet called Schumacher Levy. And again, 1993, that was discovered. It was a great decade for comets. It was pretty exciting. It was first detected on a photograph taken on the night of March 24, 93, on a telescope of Mount Palomar. And the magnitude of the comet was reported as 14. But by studying the comet's orbit, the astronomers knew that the comet had made a very close approach to Jupiter on July 7th of 92, even though they hadn't discovered it yet. And during the close approach, the unequal gravity from Jupiter on the comet's near and far sides broke the fragile object apart. That's known as tidal force. The difference in gravity was so great that it broke it apart. It broke apart in July of 92, and 21 fragments slammed into Jupiter over a period of several days centered on July 19th, 94. They hit at a speed of 36 miles per second, causing plumes and thousands of kilometers high. They left hot bubbles of gas in the atmosphere and great dark scars, which lasted for months after the collision. And those are some of those dark scars. They're about the size of the planet Earth. So those are no tiny little pimples there. The largest fragments of the comet were estimated at about 2 kilometers in diameter. And again, those are about the size of the Earth, the aftermath. It was the first time humans ever saw objects outside of the Earth, but in the solar system, collide. And scientists gave it the very impressive name of extraterrestrial collision of solar system objects. And by the way, Schumacher was the answer to a final Jeopardy question this week. So, you know, if you knew your astronomy, you could have guessed the final Jeopardy. I was surprised. 2 of the contestants actually got it right. This is a composite image of incoming fragments of the comet. So they took a bunch of pictures of the fragments coming into Jupiter, and pasted them together just so we could see this great picture. A lot of power there. Well, from here on in, we're going to look at objects that were formed by dying stars of one way or another. And just checking my camera, make sure you're still getting a good picture there. I really have a jury rig set up to do this Facebook Live today. I got to find a better way. Anyway, we're going to look at objects that were caused by dying stars of different sizes. And one thing, when you talk about stars, it's always good to take a look at the Hertzsprung-Russell diagram, or HR diagram. This was a major step in our knowledge of stellar evolution. They noted that when the luminosity, which is the absolute magnitude, which is the y-axis on the left, when you plot that against the temperature, or the stellar classification of the stars aren't randomly distributed on the graph, but they're mostly restricted to a few well-defined areas. And the stars within the same regions have the same characteristics. So as you go down from the bottom to the top, the stars get brighter. So if you look at any given temperature, it makes sense that the larger the stars you go up top, the brighter it gets. And so you see the massive, hottest, youngest stars on the left, and then you see some of the coolest stars on the bottom right. Red dwarfs and brown dwarfs, and some white dwarfs to the left of those, but near the bottom. It's kind of like the periodic table of elements, where it groups elements by characteristics. But the difference here is that when after a star leaves the main sequence, after it becomes unstable, its characteristics change, and so it actually changes its position on the HR diagram, as we're going to see. But the main sequence is that big ribbon that you're seeing going from the bottom right to the top left. That's the main sequence. That's when a star is stable. And if you take a look, you can see that the sun is right here. That's the sun. Pretty average everything. One solar mass.
Oh, now we can see.
So that's the sun.
It's a delay.
So the sun's about 5,800 Kelvin, and the mass and the luminosity of the sun are what others are measured by. So the mass of the sun is one solar mass, and the mass and the luminosity is one solar luminosity. This shows how the sun leaves the main sequence. The sun's about 4.6 billion years old, and in about 5 billion years, it's going to leave the main sequence. What happens is, as we stars up to about 5 solar masses, or 5 times the size of our sun, will all die in the same way. They start out as a protostar out of gas, and once fusion begins, the gravity continues to make the star shrink until the outward radiation stabilizes it, and it comes into what they call hydrostatic hydrostatic equilibrium. I couldn't think of the word for a minute. Right, so it's a balance between gravity and radiation, and when a star reaches hydrostatic equilibrium, it just sits there for a long time. In the sun's case, about 10 billion years. Up top, where the stars are much hotter, they burn out quicker, and they could start their death throes within a couple million years. All the way on the bottom right, if you have a brown dwarf, they estimate a brown dwarf's life at 1 trillion years, and since the galaxies, since the universe is only under 14 billion years old, we really haven't seen a brown dwarf die. So that estimate is going to have to stand for a while until we get some proof of that. So then, once the sun burns up all of its hydrogen, it starts burning helium, and as it gets near the end of helium, it starts to, the radiation starts to win over the gravity, and the sun becomes a subgiant. And when it starts burning helium, it becomes even bigger, into a red giant. At that time, all of the stars up to Mars and possibly Jupiter will be inside the sun. And what happens is, after a while, the sun will blow off its outer shell and create what's called a planetary nebula that will last for a few tens of thousands of years. And the star itself, about half of the original mass of the sun, will turn into a white dwarf, no longer gaining energy from fusion, but just getting cooler and cooler over billions of years. So what I'd like to do is take a look at some of these remnants of stars that are approximately the size of the sun, or slightly larger, and look at these planetary nebulas, because they are quite impressive. This is the Ring Nebula. It's about 1,630 light years away in Lyra. It's a face-on ring, so we could see it. It looks like a little cigar smoke ring in the sky when you see it in a telescope. You don't see those colors when you're looking at it with your eye. Again, you need the camera's long exposure to really get that kind of a color. It's a very ordinary glowing remains of a sun-like star. There's a 15th magnitude star right in the middle. You can see it. And again, the heat produced is no longer by nuclear fusion, but just because it's super high density. About a metric ton per cubic centimeter is how dense it is. And that gravity alone will help keep that thing hot. And The colors are artificial colors. A lot of the colors that you see when you see astronomical pictures. Some are done for artistic reasons. Others are done by scientists to color code different elements. So in this color, blue color is helium, and the cyan of the inner ring is the glow of hydrogen and oxygen, and the reddish color on the outer ring is from nitrogen and sulfur. This ring is about 1 light year wide. And as I said, the planetary nebula phase lasts a few tens of thousands of years, say 30,000 years or so. Really a mere drop in the ocean when you figure that the life of the sun will be 5 billion years. Now, if you remember back to the beginning of our talk, I talked about all the different wavelengths scientists look at an object at. So let's take a look at this ring nebula and add a few more wavelengths to it. There it is. There's the same, that inner part is the ring nebula we were looking at, but look at all the extra detail that we get through the infrared. Around 2.1 micron and H alpha are added here. I mean, you can almost feel the shock wave running through those through that outer ring of gas. And that outer halo shows us the residue of the stellar winds that were ejected during the star's red giant phase about 10,000 to 100,000 years earlier. And again, the picture was made by combining images from the Hubble telescope, the Large Binocular Telescope, and the Subaru telescope. And just a little trivia, Subaru is Japanese for the Pleiades. So that's why you'll see the stars on the Subarus, because that's supposed to be the Pleiades. And there's only 6 stars because the 7th sister was supposedly invisible. That's why there's only 6 out of the 7 sisters. This is the Dumbbell Nebula in Vulpecula, about 1,200 light years, first described by Charles Messier in 1764. And he made a catalog, the Messier Catalog. And what he was really doing was looking at these objects as nuisances. He was a comet hunter. And there were a lot of these faint, fuzzy objects in the sky that distracted him from comet hunting. And so he made a catalog of them, so he knew when he came upon them that they weren't comets and he should just keep moving on. And I guess he didn't have any infrared stuff or good enough camera, but he sure missed some great stuff. Here's a really cool one. This one's called Hubble Spirograph. And this image was taken around the year 2000. And its official and much more boring name is IC418. But it just glows like a multifaceted jewel, I think. It lies about 2,000 light years from Earth in the direction of the constellation Lepus. And again, the picture has been enhanced to designate different camera filters used which capture different elements. But a very pretty object. Now this next object, this planetary nebula, qualifies both as a beautiful and a strange object. It's called the Cat's Eye Nebula. And by the way, planetary nebula has nothing to do with planets. It's just that they resolve into disks, so they remind one of a planet. Stars will not resolve. They are always pinpoints of light, but these objects actually take up space when you're looking at them. And like when you see the smoke ring of Lyra, it looks like a fuzzy little planet. Now the reason why I say this is strange is because if you look carefully, you'll see that there's 11 concentric rings, or they're actually shells, around this cat's eye. So each ring is actually the edge of a spherical bubble seen projected onto the sky. So it's like if you had an onion and you cut that onion and then looked at the onion, you would see all those rings. That's what you're looking at. Each one of these rings is actually a bubble that surrounds the star and the nebula. It's just wild, and scientists have no idea what caused that type of pulsation. It looks like they were formed at 1500 year intervals. And these convulsions created dust shells, each of which contain about as much mass as all of the planets in our solar system, which still is only about 1% of the sun's mass. But very odd configuration. The bullseye patterns seen around the planetary nebula come as a surprise because they had no expectations that episodes of this kind of mass loss at the end of a stellar life would repeat every 1500 years. And there's all kinds of theories. This is a good one to look up on Google. Cycles of magnetic activity, action of a companion star orbiting it. The material was ejected smoothly, and somehow there was something created a magnetic field that disturbed it. Luckily, I have not heard an alien theory, but I'm sure those are out there on some of the sketchier astronomy sites, or maybe they're astrology sites. I don't know. But just amazing. And again, the star that created this is very similar to our sun. Had the same kind of life as our sun, became a red giant, and then as the outer atmosphere drifted off, it left a white dwarf in the middle and these really weird concentric shells that we have no idea. So sometimes these stars of less than 8 solar masses are called dwarf stars because they end up as dwarf stars. It's a dead core of a star about the size of a sun, and but very, very dense. It could weigh as much as half of its original mass, but with only approximate size of the Earth. Yeah, I think I just said it was the size of the sun. It's about the size of the Earth, but with about half the mass of our sun. Right, so our sun is so large right now that about 1,300,000 planet Earths can fit inside of it. So imagine half of that, 650,000 planet Earths in the space of an Earth. It's just super, super dense. And the stars are still very hot. Ultraviolet and other wavelengths flood out of their gas shells. They light up the gas shells. As you can see, all that gas around it, all those concentric rings are all lit up by the radiation of that dwarf star. Here's a couple of slides I have left over from my Halloween talk. I figured we'd keep them in there because they are pretty. This is known as the Little Ghost Nebula. It's round and it's very faint. It's NGC 6369. It was discovered in the 18th century by astronomer William Herschel as he used a telescope to explore the constellation Ophiuchus. The nebula's main ring structure is about a light year across, so it's about the size of the ring nebula in Lyra. And we see ionized oxygen, hydrogen, nitrogen, just as we see in other ones. It's about 2,000 light years away from us. Here's another scary one. This is the Ghost Nebula. It's a reflection nebula, so it wasn't. This wasn't caused by a dying star, and it's in the Cepheus constellation. It's located about 1,500 light years away from Earth. I like this picture. It's the same one. Believe it or not, this is the same object. The Ghost Nebula it's considered a globule. It's over 2 light years across, and there are several stars embedded in there whose emission make the nebula shine with that brownish color. A little wider field view of the Ghost Nebula shows it with little goblins. So this is the entire region around the Ghost Nebula. And as I said, that was my Halloween slideshow. This is one of my favorites because this, again, is ultra beautiful and scary as far as the power that's represented here. It's called the Butterfly Nebula. And this nebula is found in Scorpius, and it's known as a bipolar nebula. And one look at it and you can tell why. It has one of the most complex structures observed in a planetary nebula. And although it does look absolutely gorgeous, there's tremendous power behind this beauty. The spectrum of its center star shows it to be one of the hottest stars known, with a surface temperature of about 450,000 degrees Fahrenheit. Compare that to our sun at just under 10,000 degrees Fahrenheit. So we're talking about 45 times hotter than our sun. And this is a dying star, remember that. I mean, this star must have been a really, really big star. And currently it's only 64% of the mass of our sun, but this thing must have been humongous. Not humongous, a big star, sorry. I'm getting carried away with myself here. So the central star, you can't even see it. It's hidden with a donut-shaped ring of dust, as you can see it. It almost looks like the caterpillar body of the butterfly. And so that dust appears as a dark band pinching the nebula in its center. And you can see that dense equatorial belt of dust and gas, which astronomers feel is the cause for the nebula's bipolar shape. The outflows are they are roiling cauldrons of gas, heated to more than 36,000 degrees Fahrenheit and racing across space at about 600,000 miles per hour, fast enough to get from here to the moon in 24 minutes. So again, the gas itself, the cauldrons of gas that are shooting out of this thing are 3-4 times hotter than our sun is. I mean, this is just an amazing object. All right, so far, we've looked at the remnants from stars about the size of our sun and a little bigger, called planetary nebula. And that takes the top path, right? From stellar nebula to an average star to a red giant to a planetary nebula, and then 30,000 years after that, we're left with a white dwarf. So if a star is 8 times or bigger, very simply, the star's mass won't experience a helium flash. It'll just keep fusing elements and won't stop at carbon and oxygen. Now, because of the higher pressures, these stars just keep growing bigger and bigger, up to 1,000 times the size of our sun. And you know, they may burn hydrogen for 10 million years, helium for 1 million years, carbon for 1,000 years, and so on, until they get to iron. Iron is the hard stop, as we say. You don't get past iron. And the reason for that is the product of the reaction of elements up to iron has less mass than the reactants. But when you fuse iron, the product of the iron fusion has more mass than the reactants, right? So therefore, iron fusion does not create energy. Instead, it requires the input of energy. And so when iron builds up in the core of a high mass star, it's a catastrophic consequence. I mean, there's a little back and forth, and it happens very quickly. When iron shows up, we're talking minutes. It's hard to imagine something that large reacting in minutes. But what happens is it just collapses inside itself, and then you have a supernova explosion. And it's just amazing. It's an explosion that one supernova can outshine an entire galaxy. And yes, this chart is a bit simplified. As a matter of fact, the whole classification of supernovas needs to be redone. It's just our technology has gotten so advanced. We see many different types of supernova, and we need to just scrap the whole classification system. But it's gonna take a while. It's kind of like the U.S. going to the metric system. You know, we know it's got to be done, but you know, it's a lot of work, and we're just slackers, I guess. Probably a lot of politics too. But so understand, this chart is certainly relevant, But the story behind star evolution is much more intricate than this shows. But as we go down the bottom, we have a massive star, and that turns into a red supergiant after, and then from that we get the supernova, and depending on the mass of the star, we're either left with a neutron star or a black hole. So these explosions are so bright that they're visible at immense distances, right? If a nearby star were to undergo a supernova explosion, it would be so bright that it would be visible during daytime. And, you know, I don't know if you watched the hype over Betelgeuse. You know, it's going to go supernova any day now. That's kind of what would happen. We'd see it during the day. In modern history, no supernova has gone off close enough to be visible during the daytime. But two famous astronomers, Tycho Brahe and Johann Kepler, both observed naked eye supernova within their lifetimes. In 1987, a supernova went off about 50,000 parsecs from us, which is about 160, 170,000 light years. And this is the ground-based telescope image of that supernova 2 weeks after the explosion. It's on the bottom right, and you can see how bright it is. The film just does not capture the difference in brightness between that star and the rest of the galaxy, because it did outshine the galaxy. And this is not a picture. This is just an artist's rendition of a core of a massive star collapsing and then bouncing off, causing a huge shock wave, and in just a few seconds causes a huge explosion known as a Type 2 or core collapse supernova that blows off most of its outer parts. And again, these explosions are so powerful that they can actually outshine the entire galaxy, outshining billions of stars. These explosions leave behind a super dense core, even denser than the white dwarf we were talking about, and known as a neutron star. A neutron star can have a mass greater than our sun, but only be 12 miles or so across. Right? So the sun weighs about 333,000 times more than the Earth. So imagine the mass of 166,000 Earths packed into the space of the size of Manhattan, right? Manhattan's about 12 miles. So imagine 166,000 Earths packed so tightly that they fit into the space of Manhattan. We're talking about 1 trillion times more dense than the sun. Here's a Hubble photo of my favorite neutron star supernova remnant, the Crab Nebula, also known as M1. And notice it's the difference between this and a planetary nebula. There's so much more intricate tendrils and details in this. This is actually a mosaic image, one of the largest ever taken by the Hubble Space Telescope of the Crab Nebula. It's 6 light years wide and still expanding. And the supernova explosion was recorded by Japanese and Chinese astronomers in the year 1054. So that's what I find really cool about this remnant, is that there were people on this planet looking up in the sky and they saw it. And then they saw the supernova shining in the daytime. And they took notes and recorded it so that we know when it happened and that people actually saw it. It's now magnitude 8.4. You know, to be seen in the daylight, it's got to be brighter than Venus. The orange filaments are tattered remnants of the star, consisting mostly of hydrogen. And the rapidly spinning neutron star embedded in the center of this nebula is like a dynamo powering this entire eerie, bluish kind of glow. I mean, there's so much radiation coming that this is lighting up this 6 light year wide area with its radiation. The blue light comes from electrons whirling at nearly the speed of light around a magnetic field, which is created by the neutron star. And the neutron star itself is like a lighthouse. It ejects twin beams of radiation that appears to pulse 30 times a second due to the star's rotation. This thing is spinning crazy fast. And that's why it's known as a pulsar, because if you see these pulses of energy 30 times a second, you get radio pulses, and that's how a lot of these pulsars are discovered. This is a beautiful photo of the crab detail. It shows us a stripped away view. The pulsar is a bright star on the right side of the pair, near the middle of the photo. And you can see bright wisps moving away from the pulsar at an estimated half the speed of light, forming an expanded ring. So you can see those ripples. These are wisps of highly energetic gas gathering along magnetic field lines created by this rapidly rotating neutron star. One interesting star I'll just throw in, I don't know a whole lot about this one, but I love the name. It's the Black Widow Pulsar, and it also has a boring name, Pulsar PSR B1957 plus 20. It's a dangerous partner to have. It weighs as much as 2 suns, only about as wide as Washington, D.C., which is smaller than New York. And it's getting bigger by feeding off its mate, which is a lightweight brown dwarf. And the 2 stars orbit each other about every hour and a half in a very deadly close dance. And this is an actual photo taken in X-ray and also optical, which is the green-blue. And it was made possible only by using a gas cloud as a magnifying glass. Really interesting stuff. This is another one to look up, the Black Widow Pulsar. And, you know, what a feat to use a gas cloud as a magnifying glass. It's kind of like seeing this. It's kind of like seeing a flea on the surface of Pluto from Earth. And this is 6,500 light years away, and it's a very recent photograph, May 2018. The pulsar's beam strips layers away from the star, and which pulses and then slurps it up. Oh yeah, it also the pulsar spins 600 times a second. So it's known as a millisecond pulsar. So it's just a very bizarre and powerful object. This is just a artist rendition again of what the Black Widow might look like with its 2 jets, and you see the gas that's been stripped off is formed a halo around the brown dwarf, which is in the foreground. The brown dwarf star is about 1/3 of the diameter of our sun, so maybe 1.2 million miles or so. But these two are very close together, about 2 million kilometers, and compare that, the distance from Earth to Sun is about 150 kilometers. So these 2 stars are awfully close. That's just another picture showing the shock wave of these 2. I just thought it was a cool picture. Another artist rendition. Same pulsar, 1,000,000 times closer, showing the effect of its wind on its companion star. The wind from the pulsar blowing back the gas that's evaporating off the pulsar. The bow shock is much too large to be shown. If it was shown to scale, the bow shock that you see here would extend 15 miles off the edge of your screen. So just enormous shock wave there. And that brings us to our final. We take the bottom route again to supernova. When you get to a really, really massive star, somewhere over 80 solar masses, up to 80 solar masses, a neutron star is left behind. But for the really humongous stars, and that is a scientific word, I think, they collapse into a black hole, we think. You know, we're now in the area of heavy duty theory, obviously. I just threw this slide in because it has another strange object. There's a quasar, which is the most luminous of known quasars in the early universe. And it seems to be powered by the most massive black hole detected in that cosmic area. Scientists have determined that the quasar puts out energy about 420 trillion times the rate of the sun. So how's that for a little power? The astronomers estimated the black hole's mass in two ways. They first extrapolate from the quasar's total luminosity, and then by measuring the speed of clouds that orbit this behemoth. Both methods that they use to make the assumptions and simplifications give a mass of about 12 to 13 billion solar masses. What makes it really strange in my eyes is that no one can explain how something that large could have formed when the universe was only a mere babe at 875 million years old. And that's been the subject of many, many articles. This is just an artist's rendition of a black hole and its accretion. I'm going to speed on because I'm taking a lot of time here. This is another artist's rendition of a black hole. And although we can't see black holes, we can see their effect. And black holes are so massive that they bend the fabric of time and space. And we can see this in the stars whose light paths seem to get elongated and warped. And as we'll see in a couple slides, they can also act as lenses, as gravitational lenses, and magnify objects that are behind them. This, of course, this picture was in the news. It's a picture taken, or actually it's an aggregate of many, many pieces of data collected in an array called the Event Horizon Telescope. And it's the first supermassive black hole that we've observed, or actually we've observed what we think is the event horizon in the heart of M87, about 55 million light years from Earth. And over the course of 4 nights in April of 2017, they gathered the data, and then it took a long time to write the algorithms to put the data together so that we can actually see that. And there's the black hole's home. That's M87, about 55 million light years from Earth. So take a look at these elongated objects. They're giant lensed galaxy arcs. Those are, in the middle of this picture is a very, very massive galaxies and of course black holes. And the mass is such that it distorts galaxies behind it and brings it out to the sides. And so that we see a galaxy that's been warped into a nearly 90-degree arc of light by the gravity of the galaxy cluster, which is known as RCS2, and a whole lot of more letters, about 5 billion light years away. The coolest gravitational lensing, I think, is Einstein's cross. Now, Einstein predicted gravitational lensing many years ago, but now we're seeing it all over the place. You know, when Hubble first went up, we started pointing it in areas that we thought were not occupied, that didn't look like there was anything there, and we marveled at how many thousands of galaxies Hubble brought into view. But now we're taking the opposite approach, and we're pointing towards areas that have massive amounts of galaxies and black stars. And we're starting to see all of this gravitational lensing, and it's just so cool. This Einstein's cross that you see here, if you look at those arrows, they're each pointing to a little yellow star. What you're seeing here is the large cluster galaxy has split the light from an exploding supernova in a magnified background galaxy into 4 yellow images to form the Einstein cross. So those 4 images that form the cross are all the same light from the supernova just taking different paths around this super massive galaxy. And scientists, I don't know how they figure this math out. They think they're going to see another piece of this exploding supernova in about 5 years. So I don't know how they figure out the path it takes and all that, but I think the Einsteins cross is just such a very cool example of gravitational lensing. So I'm going to wind it down. Oh, there is a smiley face for you. I'll include him just because he's cool. One last gravitational lensing photo. Gravity's Grin, it's called. And it's a combination of X-ray and optical image data from Chandra and Hubble Space Telescopes. It's also nicknamed the Cheshire Cat Galaxy Groups, all kinds of imaginative names. It's about, it's just under 5 billion light years away, 4.6. Pretty cool example. So look, thanks a lot for staying with me this long, if indeed you have. Thanks for visiting UCNJ, United Astronomy Clubs of New Jersey. Please visit our website, uacnj.org. You'll find out when our observatories are opening up. And usually at this point in the night, we all go outside and we look through telescopes, especially on a beautiful night like this. Like us on Facebook, follow us on Instagram. Visit our observatories once we're open to the public again. Check our site for details, and you'll also check our site to find out what we're going to talk about on these Facebook Live sessions. Also, we'd really appreciate your support. We just finished raising $10,000 to put this telescope that you see on the right in a home. This is its old home, but this was donated to our club. It's a 25-inch telescope. It's going to be amazing. We just raised $10,000 to build the shed for it, and we've got a bunch of other telescopes up there, so you can just walk around from telescope to telescope and see what people are looking at. It's a very cool place to be. You can mail any donations to the address on the screen. You could also donate using PayPal or credit card on the left side of the UACNJ website. So thank you very much for listening. And I'm kind of deaf here. I don't have ears. I have a really weird setup, but I'm going to, next time I do a talk, I'm going to have a better setup for sure. But thank you very much for listening in, and I appreciate your time.